All right, guys, let's talk about some aromatic chemistry. So this deals with chapter 17. This deals with aromatic compounds. And so that name aromatic has a variety of different meanings, but all the compounds we're going to talk about were named aromatic at first because they tend to have rather pleasant smells. But what we tend to mean in the chemistry world when we say aromatic compounds is that they are unusually stable compared to non-aromatic compounds. And sort of the classical aromatic compound that people talk about the most is benzene. That's one you may have already seen before, but the benzene typically is represented as a six-membered ring with three alternating double bonds. So we have double bond, single bond, double bond, single bond, double bond. So, but you know, if you think back to resonance structures, of course, this drawing of benzene is as equally valid as the one that migrates the double bonds around that ring. So it turns out we can draw two different resonance forms of benzene, and what we know about resonance forms is that the true structure of the compound is somewhere in between those things. And that's evidenced by physical properties of benzene in that all carbon-carbon bonds are the same length. And so that can't possibly be true if we have an alternating single and double bond situation, right? The single bonds would be longer than the double bonds. But in reality, because benzene is a blend between these two resonance structures, all the carbon-carbon bonds are exactly the same length, somewhere between a carbon-carbon double bond and a carbon-carbon single bond. So you'll frequently see benzene drawn, particularly in the older literature, like this, where we just draw the six-membered ring with this donut in the middle, and that's meant to be sort of all six of the pi electrons having full access to all six carbons of that system. Okay, so that benzene is an example of an aromatic compound. Let's talk a little bit about nomenclature in terms of different types of substituted benzene rings, because this is a case where these are frequently encountered compounds and they all sort of have common names. So we just talked about benzene. If you take what you probably would try to name as methylbenzene, if you hang a methyl group off of a benzene, that becomes a very common solvent, toluene. Of course, I can't write that because it's getting late tonight. Toluene. So toluene is the name of methylbenzene. It's a very commonly encountered solvent in organic chemistry. Other common substituted benzenes include things like benzoic acid. If you have an aldehyde instead of a carboxylic acid, you get a compound called benzaldehyde. This, like I said, was benzoic acid. I love benzaldehyde because it smells just like cherries. It smells like sort of a cherry Jolly Rancher. I've never really had the guts to taste it, but it sure smells like a Jolly Rancher. Other common ones that you might run into in the literature, if you have an alcohol group directly attached to a benzene ring, that compound's known as phenol. And if we have a methoxy ether attached to a benzene, that material is called anisole. Okay, so I'm obviously not going to test you on these common names, but as you read chemical literature, you will see them come up pretty frequently. You'll never see, for instance, somebody write methyl benzene. They'll always write toluene. The next part is something that I really do want you to focus on, and that is the relative arrangement of di-substituted benzenes. This is important because we will refer to these relative positions when we talk about benzene reactions. So if you think about having two things attached to a benzene ring, there are really only three ways in which you can do it. You can have those two substituents right next to each other on adjacent carbons. That's what we would call an ortho arrangement. If you skip a carbon in between the two things, what you would have there would be methyl group here, methyl group here. That is what we would call a meta arrangement. And then the only other way that we could arrange things is on opposite ends of the six-membered ring. And that arrangement is what we call a para position. Turns out that a benzene ring with two methyl groups attached to it is called a xylene, and so we can use these designations ortho, meta, and para to designate the different xylenes. So you would call this orthoxylene, metaxylene, and paraxylene. But I really want you to focus in on the meta, ortho, and para arrangement and how those substituents are oriented relative to that ring, because we're going to come back to this when we start talking about reactions of benzenes. So we can look at just a few simple examples here of how this shows up. So if we take, for instance, a benzene ring that has two chlorines attached to it, I would call this meta dichlorobenzene. We can take a toluene, for instance, and plop a bromine in this position. We would call that para-bromotoluene. And then just as a last example, if I were to take a phenol and, for instance, have a chlorine attached right next to it, what we would have at that point then is an ortho chlorophenol. But the point we're trying to make here is just this relative arrangement of the two groups on the ring. So this is a meta arrangement, this is para, and this is ortho. So these things are going to become important when we start thinking about taking a substituted benzene and adding another substituent to it. We'll find that we can actually preference the formation of one or more of these types of orientations. Okay? All right, so we talked about one thing about aromatic compounds being exceptionally stable. And so we're going to look at that in the context of benzene. Let's go back to blue. So we're going to look at the aromatic stability of benzene, and we're going to look at this through looking at the heats of hydrogenation. So what does that mean? So if I take a single carbon-carbon double bond and I do a reaction you guys learned in sophomore organic 1, I treat that with palladium on carbon and hydrogen, I can hydrogenate that carbon-carbon double bond. I can convert that alkene directly to the cycloalkane. I can get cyclohexane. Well, that's an exothermic reaction, and so I can measure the amount of energy that's released during that reaction, and that gives me a sense of how stable the compound is, right? The more energy that's released, the less stable the compound is. So it turns out you can go in the lab and you can measure the enthalpy of that hydrogenation, the delta H. And if you take one carbon-carbon double bond in cyclohexene and hydrogenate it, you would measure the release of 120 kilojoules per mole of energy. Okay, And so if you start thinking about adding double bonds to this system, it should, in theory, just be an additive process. If I add more double bonds, I should see a doubling of that heat of hydrogenation, since this is an exothermic process. All right, so if I get 120 kilocalories of energy for hydrogenating one double bond, if I take a diene like this one and I hydrogenate both double bonds, I would expect to double that energy release and see 240 kcals per mole of kilojoules per mole of energy, and that's exactly what I see. Okay, so right now it's completely additive. If we carry this analysis forward, though, with benzene, so now we've got 3 carbon-carbon double bonds, what I would expect is if I have hydrogenating 3 carbon-carbon double bonds, if this whole process is additive, reducing all 3 of those carbon-carbon double bonds to give me cyclohexane would give me a delta H expected of 360 kilojoules per mole, right? So that's just triple what we got for the single double bond. This is what we would expect, but in reality, we get something different. In reality, it turns out to be much harder to hydrogenate benzene than just using palladium and hydrogen. In fact, you can't do that. So it actually turns out that if I take benzene and I want to convert it to cyclohexane, I actually have to really beat on this reaction to get it to happen. I need to use hydrogen gas, but I need to use 100 times the pressure that I would use for the other hydrogenations that we just talked about. So 100 ATMs of pressure of hydrogen. I need a more reactive nickel catalyst, and I've got to soup this reaction up even more by heating it to 150 degrees C. So already these conditions suggest that benzene is more stable than you would expect. And then that's borne out when we actually calculate and measure the delta H that we get out of this reaction. We only get back 208 kilojoules per mole, right? And so what this conclusion is, based on the expected versus the reality measurement, we get a whole lot less energy out of the reduction than we would expect. The conclusion here is that benzene is more stable than we expect. So benzene's a lot more stable than we would expect, and so the question is, why is that? That has to do with the fact that benzene is aromatic. So we get this extra stability because benzene is aromatic. And so there are some criteria that we can look at for other molecules to see whether or not they obey this aromatic rule and have this enhanced stability. We're going to return back to why this is so stable, but let's talk a little bit right now about how we can tell if something's aromatic. So we're going to look here at criteria for aromaticity. Okay, and the criteria are these. We have 3 things that we have to pay attention to. First of all, the molecule has to be cyclic. So if the carbons are not arranged in a ring, it's not going to be aromatic, period. That's the first test. If the compound's not aromatic, if the compound's not cyclic, it's not aromatic. The next thing is that we have to have the compound be planar and conjugated. Okay, and so this again is how we can ensure that all of the electrons in the pi system have access to all of the carbons in the system. That can only happen if we have a conjugated molecule and the molecule is completely planar. Remember what we mean by conjugated. That means we have alternating double and single bonds. Okay, so if we have that situation where we have alternating double and single bonds, the compound's planar, it might be aromatic. The third rule, and the most important rule, is the number of pi electrons in the system. So for it to be aromatic, it must contain what we call 4n plus 2 pi electrons. Okay, so what does that mean? That means that the number of pi electrons has to be solvable for this 4n plus 2 equation for a whole number. And we'll see some examples of that in a minute. This third rule is actually known as the Huckel rule of aromaticity. So Huckel was the chemist who noticed that that 4n plus 2 equation has to be solvable for a whole number to give me an aromatic compound. So if we pay attention to these rules and we come back to benzene, we can see right away that it's cyclic. We can see right away that it is planar because all of the carbons are sp2. We can see that it's conjugated. Again here because all of the double bonds alternate with single bonds. And then we can see that it follows the Huckel rule because I have 6 pi electrons in this system, and if I set that equal to 4n plus 2, I can solve that algebraic equation for n equals to 1, and that is a whole number. So if this fits along with the other two criteria, I can say that this is an aromatic compound. Okay? So let's look at just a few other examples to kind of drive this series of rules home. All right, so the first example we're going to talk about is what would happen if we just take a benzene ring and we smash another benzene ring next to it. We get a compound like this. That compound's called naphthalene. And so we can ask the question of, does it fit all of these criteria that we need for a compound to be aromatic? So I can see that it's cyclic. It's planar because all the carbons are sp2 hybridized. It's conjugated because all the way around this system I see alternating double and single bonds. And now I just have to count up the pi electrons. If I want to count, I would say 2, 4, 6, 8, 10 pi electrons. If I set that equal to 4n plus 2 and solve that equation, I would get that n is equal to 2. 2 is a whole number, so I can say that this compound, if I can spell this late at night, it was aromatic. So naphthalene is an aromatic compound. Let's take a look at another system. We can play this game by adding a whole nother set of a cyclic system. So I could ask the question, is this compound with 3 of these rings tied together aromatic? This compound also has a name. This is phenanthrene. And so I can ask, is phenanthrene an aromatic compound? So again, I say it's conjugated because everywhere around this ring system I see alternating double and single bonds. Clearly completely cyclic. Going to be planar because I have sp2 hybridized carbons all the way around this system. Now I can go with electron counting: 2, 4, 6, 8, 10, 12, and 14. So I count 14 pi electrons. If I set that equal to 4n plus 2, I can solve that equation for a whole number where n is equal to 3. So again, I would say that phenanthrene is an aromatic compound. As a third example, let's look at this molecule. Let's say we have a cyclobutadiene system where I now have a cyclic system that has 2 double bonds. This thing fits some of the rules for aromaticity, right? It is cyclic, it's planar, all the carbons are sp2 hybridized, it's completely conjugated. But when I go here and count pi electrons, I get 2 here and 2 here. What I have here is 4 pi electrons. Now if I set that equal to the 4n plus 2 equation, I can only solve that equation where n is equal to 1/2. This is a non-whole number, and so I can say that this compound is not aromatic. In fact, it turns out to be what we would call anti-aromatic. What is an anti-aromatic compound? It's a compound that satisfies all the rules of aromaticity except for it actually has a 4n number of pi electrons. Anti-aromatic compounds are actually especially unstable. So just to give you a sense of how unstable these things are, the cyclobutadiene molecule, it took about 100 years to isolate this compound, and it only hung around for a few seconds after it was first isolated. So these compounds are highly unstable because, again, it's an anti-aromatic compound. It's just as unstable as aromatic compounds are stable. We'll talk a little bit about why that is in just a second. All right, the next series of examples we're going to look at deals with a little bit more of a complicated system. What happens if I start to add in heteroatoms into the system? So here are 3 examples of commonly encountered compounds that do exist that sort of fit most of the bills for aromaticity, but we have to ask ourselves, do they actually count as aromatic compounds? So this is pyridine, which we saw when we were talking about the activation of alcohols into better leaving groups a while ago. This compound is called furan, and this compound is called pyrrole. And what we're going to find out is that all of these compounds are aromatic. But the question becomes, how do we account for the lone pair electrons on the heteroatoms? That's the big question, right? Because we have to know whether or not we need to count those things to help make the compound aromatic. And so in some cases we're going to find we do need to count them, and in other cases we don't need to count them. Fortunately, there are rules, so we can think about, for the heteroatoms, if we look at nitrogen, there are 2 cases that we have to worry about. If N is involved in a double bond, that's the case up here in pyridine on the left. Nitrogen is involved in a double bond. In that case, we don't count the lone pair. Okay? The second scenario with nitrogen is N is not involved in a double bond. In that scenario, we are going to count the lone pair. Okay? Then the other heteroatoms we're going to worry about are oxygen and sulfur. They're basically the same because they sit they sit right there in the same column of the periodic table. In that case, we're always going to count one and only one lone pair. And it'll become clear in just a minute why that is. Okay, so let's handle that situation with furan first. What this boils down to is we really have to think about whether or not the electrons that are in that lone pair are in the same plane and able to interact with the p orbitals that make up the carbon-carbon double bonds right? Because we have to be able to interact all those electrons together to make a compound aromatic. All right, so let's look at the case of furan. So furan, oxygen has 2 lone pairs. And what we're going to find is that if we think about aromaticity in this system, we're going to count the 2 electrons in each of these pi bonds, carbon-carbon double bonds, so that's 4 electrons, plus 1 of the 2 lone pairs. If you follow that, that's going to give us 6 pi electrons, which is solvable in that 4n plus 2 rule where n is equal to 1. So if we only count 1 lone pair of furan, I would say that furan is aromatic. And so the question becomes, well, why am I only going to count 1? That has to do with the orientation of the way that those electrons are oriented in this system. So if we think about the p orbitals that are overlapping to make those 2 double bonds, they're above and below that 5-membered ring. And we can shade those all in the same phase. Okay. What ends up happening with the electrons that sit on the lone pairs is that they, on oxygens, they actually occupy sp2 orbitals. And some of the sp2 orbitals point in a different direction. So here's 2 electrons in the lone pair, and here are 2 electrons in a lone pair. And it turns out that this particular lone pair that's coming above the plane of the 5-membered ring can overlap with these other orbitals that make up the extended pi system. So if all of these guys overlap together, I have 6 pi electrons in that system that are all in the same plane and interacting. And so in this case, I have 6 pi electrons that are giving me the aromaticity, and this is in what we call an orthogonal orbital. That's a big word to say that it's pointing in the wrong direction to interact with the rest of the pi system. So those electrons don't count because they can't possibly overlap with the p orbitals that we need to make up the aromatic system. Okay, so that's why we only count 1 of the 2 lone pairs on oxygen and sulfur. All right, let's have a look at what happens when we think about pyridine. So pyridine is going to be that case where the nitrogen is involved in a double bond. And so what we conclude from that is that we actually don't count these. Okay, so if we're going to count now electrons for whether or not this compound is aromatic or not, it's exactly the same as benzene. I count 2, 4, 6 pi electrons. Again, that fits the 4n plus 2 model where n is equal to 1. So I would conclude that pyridine is aromatic. And that's exactly what we see. So again, let's see if we can figure out why that is. If we think about the way in which those nitrogen lone pair electrons are oriented relative to the plane of the pi system, we're going to find that they sit in an sp2 orbital that is opposite the rest of the pi system. So I can make up this extended pi system of orbitals where everything can overlap all together to extend 6 pi electrons around that ring without using the lone pair of electrons. That lone pair of electrons on pyridine is set perpendicular to that pi cloud, and so I don't need to use that at all to make pyridine aromatic. And that actually turns out to explain why pyridine is strongly basic, right? Because I can use those electrons in that lone pair to pick up a proton without disturbing the aromaticity of this compound. So that's why pyridine acts as an amine base. Let's compare that with pyrrole. So pyrrole is the nitrogen analog where we're going to actually have to use that lone pair of electrons to make up the aromatic system. what we'll find is that pyrrole is a really crappy base for that reason. All right, so here's pyrrole. Got 2 pi bonds and 1 lone pair on nitrogen. So this is a case where that nitrogen is not involved in a double bond, so we actually do have to count this lone pair in our calculation for aromaticity. So if I'm counting pi electrons in this system, I have 2, 4, and 6 counting that lone pair. So I would say this system has 6 pi electrons. Again, that fits the 4n plus 2 rule where n is equal to 1. So I would say again that pyrrole is aromatic so long as I count the lone pair that sits on that nitrogen. All right, so now what happens if I think about how the orbitals of this system would look? Now I've got the hydrogen on pyrrole pointing perpendicular to the pi system. And then now I've got the p orbitals that make up the 2 carbon-carbon double bonds in the system. And then what I've really got here is an sp2 orbital that holds that lone pair electron on nitrogen. And so if I think about the shading of this whole system and think about the electrons moving around there, I've got those 2 electrons in that pyrrole lone pair that can dump into the rest of the conjugated system and move around that whole ring, so that those lone pairs actually do contribute to the aromaticity of the compound. But because they're used in the aromaticity of the compound, pyrrole is a bad base. And I can say that pyrrole is a poor base because we're using those electrons that you might think about using to deprotonate something. We have to actually use those electrons to make this compound aromatic, so they're stuck there. Okay, so that's how we will handle heteroatoms in systems. The next set of aromatic compounds that we're going to talk about are a little bit of a subclass, and that is this case of aromatic anions and cations. Okay, and so we're going to see 2 examples of this. So if I take cyclopentadiene and think about removing hydrogen atoms or protons from this system, I could think about having a carbocation here, or I could think about having an anion at that position. Okay, and so if I want to think about the pi system that we have here, these are cyclic molecules. They're conjugated and they're fully planar. But what differs is the number of electrons in the system. So with the cyclopentadienyl cation, I have 4 pi electrons because I don't have any electrons in that empty p orbital that makes the carbocation. So this actually is a 4n number, which makes this compound anti-aromatic. So I would find it quite hard to make this carbocation because it's actually destabilized relative to its precursor because it's anti-aromatic. I count, however, the anion. I have 2 electrons in that anion plus 2 in this pi bond and 2 in this pi bond. That's 6 pi electrons. This is a 4n plus 2 system, and it's aromatic. And so what this means is this is a very stable anion. So what does that mean in reality? That means that cyclopentadiene is actually pretty darn easy to deprotonate. So if I take that carbon-carbon, that system and treat it with something like sodium hydride, I can deprotonate one of those hydrogens at that position to make the cyclopentadienyl anion in a pretty easy way because it's stable as an aromatic compound. We can look at the same thing in the terms of cyclic 7-membered rings. So I could think about having a cation, or I could think about having a 7-membered triene system with an anion. And what we'll see here is that our pattern is opposite. So now in the cation, I count 2, 4, 6 pi electrons in this system. That is a 4n plus 2 number, and this turns out to be an aromatic cation, and so it compares sort of the opposite of the cyclopentadienyl cation. It's not anti-aromatic, it turns out to be aromatic. If I look at the anion of this cycloheptatriene, I would count 2, 4, 6, 8 pi electrons. That is a 4n system where n is equal to 2. And so this is an anti-aromatic compound. And what that means, if we compare it to the deprotonation of cyclopentadiene, we would find that taking cycloheptatriene and trying to do this deprotonation would fail miserably. In this case, we can't deprotonate it because that leads to a very unstable anion. Whereas in the case of the cyclopentadiene, we can deprotonate it because we get an aromatic anion. Okay? Now, what I haven't really explained to you at all at this point is why these things are especially stable. We can explain the stability of aromatic compounds using molecular orbital theory. Okay, and so what we're going to look at is the molecular orbitals of benzene, and we're going to compare that to the molecular orbitals of cyclobutadiene. So benzene is aromatic. It's quite stable. And so what we're going to look at are the molecular orbitals of this system. Now, this is a little bit convoluted in that because they have a ring system, we can have what are called degenerate orbitals. We can actually have more than one way to make multiple nodes in a molecule. So we actually have to think a little bit about symmetry in this case. But I think everybody would agree that the lowest energy way that we could arrange these 6 pi orbital p orbitals in benzene would be to have them all overlapped. And that does in fact turn out to be the lowest energy orbital of benzene, molecular orbital. Now, I think everyone would also be able to predict the fact that the least stable way in which we could orient those 6 p orbitals would be to have them oriented all opposite one another. All right, so that's going to be the least stable interaction, where we have every orbital is opposite its neighbors so that we have no effective overlap. That's going to actually give us nodes that form in between all of those orbitals. So we would have this series of 3 nodes in the system. All right, so what gets a little bit hairy in terms of the molecular orbital theory for benzene is the middle orbitals that we have, right? We're combining 6 p orbitals, so we got to come up with 6 molecular orbitals, but it turns out that they're going to come in pairs in this case because they're equally stable. All right, so I've got to go from 0 nodes to 1 node, and there turns out there are 2 ways in which I can draw benzene molecular orbitals where I have 2 nodes. So the easiest way to come up with a system that has, 1 node, what am I talking about? We need 1 node here because we started with 0 nodes. The easiest way to come up with 1 node would be to have 3 orbitals on one side of this ring interacting in phase, and then just switch the other 3, okay? That will place a node right down the middle of this system. But it turns out we can also come up with a way to have a single node in benzene if we were to run that node through 2 carbons. And so what that would look like would be an orientation like this, where we have 2 orbitals in phase on one side of that node, and then 2 orbitals of opposite phase on the other side of that node. All right, because both of these orbitals have only one node, they're degenerate. That means they're of the same energy. So we would have 2 orbitals that could sit here. And as we'll see, there actually are 2 ways in which we can come up with benzene orbitals that have 2 nodes. I think, again, the easiest way to do that would be to have 2 in-phase orbitals and then switch these on the ends and then have 2 in-phase orbitals. So what does that mean? We can make 2 nodes by having these bottom 2 in phase, switch this one, and then go back to the same phase with this one, and then switch that one. And so here what that does is place the nodes through the carbon-carbon bonds. I have a node here, and I have a node here. So that's one way I can come up with 2 nodes. But it turns out I can come up with another orientation with 2 nodes if I pass one of those nodes right through the carbon-carbon atoms. So if I pass a node here, I can also pass a node here. And what that will give me are these molecular orbitals. So I'll have I'll have single p orbitals here, and then I can orient them opposite one another like this. Okay. All right, so that's another set of degenerate orbitals. But what you can see here in this system that I've now highlighted in purple, now I've got 6 orbitals that I can place electrons in. Here, 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 and here. Got 6 pi electrons to put in. I can put 2 here, and I can put 4 in these degenerate orbitals, and then I leave the remaining 3 higher energy orbitals empty. But what you can conclude from that is that this is going to be a stable interaction, because as I come up with energy, all of the orbitals are in the lower, all of the electrons are in the lower energy orbitals. They're all paired, and the bottom half of the orbital diagram is populated and the top half is not. So this is a good example of a stable molecular orbital diagram for an aromatic compound. All right, let's compare that to an anti-aromatic compound, cyclobutadiene, and see what happens when we think about making those orbitals. So if I think about cyclobutadiene, the easiest way to draw 4 orbitals in phase, or the lowest energy way would be to have all 4 orbitals in the same phase, right? So that's going to comprise the lowest energy level of the molecular orbital diagram. I think everybody would agree that the highest energy one is going to be the situation where all of the orbitals are opposite one another. So it'll look like that. And then what we'll see is so if I think about that one, I've got 2 nodes here. I've got a node that passes through here, and I've got a node that passes through here. We will see that there are 2 ways in which we can have a single node coming through this system. So I could have both orbitals like this and pass a node through the neighboring 2 carbons. So this is one particular orbital. And then the other way to do that would be to pass a node through the bonds instead of through the atoms. And I think that's an easier one to come up with, where those 2 pi p orbitals are opposite. So I can have these 2 in phase and then these 2 opposite. Okay. So what these are two homes, two other orbitals where we can place electrons. So again, we need to think about what happens as we go up in energy, and we need to remember that we have 4 pi electrons to place. Here is where we see the difference in an anti-aromatic compound versus an aromatic compound. So remember, this is an anti-aromatic compound. So I should see something in the molecular orbital diagram that tells me why this is unstable. So let's populate this system with 4 electrons. I can put 2 in this lowest energy orbital. And now I've got 2 to disperse between these 2 degenerate orbitals. And if you remember from Gen Chem, the way we distribute electrons in degenerate orbitals is we fill orbitals before we pair electrons. So actually the way I would populate the remaining 2 electrons in this system would be to put 1 in each orbital. And so this is the part that should give you a red flag. These are unpaired electrons. And as you can remember, unpaired electrons lead to things like radicals. So this is sort of like has diradical character, so relatively unstable material. And so that kind of can tell you why this is less stable than benzene, where all of the orbitals populate in a happy way, where all of the electrons are in lower energy orbitals and they're all paired. That's an aromatic compound. Anti-aromatic compound, you'll always have unpaired electrons filling up the higher energy orbitals, and that is what gives us the hint that these are less stable. All right, that's it for this chapter, chapter 17. This is it for testable material on Friday. I will give you another lecture on Wednesday that will start with some reactions of benzene, but that will not be on your test. Take a quick look at Canvas for a problem set that sort of gives you some practice with determining whether something's aromatic or not, and that's where the test will end. I will see you guys with another lecture on Wednesday. Hope you guys have a great night.